This is PHA filament. It's fully biodegradable, non-toxic, heat-resistant up to 100 degrees C, non-hygroscopic, prints warp-free, and promises good mechanical properties. Sounds too good to be true, right? Or could it be a serious, eco-friendly competitor to our regular ABS, PETG, and PLA? Let's find out using mechanical testing here at JanTec Engineering. Part of this video is sponsored by PCBWay. Also, thanks to Prusa Research for sponsoring my new studio. It's getting better and better and helps me create all these videos. PHA stands for Polyhydroxyalkanoate and is a bioplastic made by microorganisms, not oil. You'll find it in packaging, agriculture, and some medical applications. In 3D printing, it's still rather uncommon, but Polar Filament and Ecogensis biopolymers are trying to change that. I've been testing a lot of different filaments since starting this channel. Many were interesting, but not special enough for their own video. When Mitch from Polar Filament handed me half a spool of their PHA at 3D Printopia 2025 and told me about the properties, it caught my attention. I might be a little late to the party. Michael from Teaching Tech covered PHA about a year ago and Thomas Sandladerer tested it 8 years back. Still, the material has improved and it's worth a fresh look and detailed test. So, why did PHA catch my attention? The key selling point is its certified biodegradability, which is for sure impressive, and we will get to that later in the video. But honestly, the everyday perks are what made me excited. It's hydrophobic, meaning it doesn't absorb moisture and doesn't need drying. It offers ABS-like temperature resistance and prints on a cold bed with no warping. Of course, no filament is perfect, so let's print some samples, run mechanical tests, and see how PHA compares to PLA, PETG, ABS, and engineering filaments. Quick info about the filament I'm testing here. It's from Polar Filament, sold in their online shop for $39.99 USD per kilogram, and available in 6 colors. It carries a 6691 Marine Biodegradability certification and is sourced and manufactured in the United States. There are cheaper PHA options out there, but some use additives or blends that can affect biodegradability, and they may not be certified. I started with a bend sheet to tune the settings. In the slicer, I took a PLA profile, set the bed to 0 degrees C and ran the nozzle at 210 for the first layer and 195 for all the other layers. Exactly as recommended. I also lowered the max flow to slow the printing down. They recommend putting frog tape on the bed. I used regular painter's tape instead. Adhesion was good and the bend sheet looked great. So it was time to print the samples for the mechanical testing. My first G-code somehow messed up my filament settings. Well, that's how it looks when your PHA doesn't stick properly. With the correct settings and a cool bed, I restarted the print using the sequential printing feature where the printer completes each individual object. Parts still warped, so I decided to go with such a tape. It has a smoother surface and seems to be similar to frog tape. With the purple tape, parts stuck really well and my adhesion issues were gone. I also tested printing PHA on top of a layer of PLA since I did a similar trick with ABS in a past video and it worked very well. PHA and PLA seem to be compatible, which makes sense as some manufacturers blend them in their filaments. I printed PHA on top of a raft made from PLA and it worked nicely. If you want me to dive deeper into such combinations, let me know in the comments. All samples printed cleanly in the end, with minor warping on a couple pieces, but nothing that affects testing. Some tape stayed on the underside, which is also fine. I left the specimens to air overnight before testing. Fresh PHA feels a bit soft right off the printer, giving it time helps it crystallize and reach its final hardness. Quick reminder, so far only a small percentage of you are subscribed. If you like deep dive filament tests with real data, consider subscribing, it really helps. Thank you. Let's dive into the mechanical testing. The tensile test can be used to analyze two interesting properties: the strength of the material, referred to as the tensile strength in the XY direction, and the layer adhesion, in other words, how well the individual layers stack during printing bond to each other. This is then referred to as the tensile strength in Z direction. For the test, I printed 4 of these samples in a lying position and 4 in standing position. I then pulled them apart with my DIY tensile testing machine, measured the force with the load cell and put all the measurements in an Excel spreadsheet. The tensile strength in megapascals, which is tensile force per area, is then automatically calculated. Here you can see the results of PLA in XY direction compared to other common materials I tested before. What I found to be interesting is the way the samples broke apart. It is usually a sign for rather bad layer bonding, which got approved by the test in that direction. As expected, it's rather low, which is a pity. One could improve it by playing around with printing temperature and part cooling settings, but I usually don't do this in these tests as I want to compare recommended print profiles. Let me know your thoughts or experiences in the comments. Now let's move on to the next test, my 3-point bending experiment. It can be used to determine the bending modulus as a measurement of the stiffness of the material. To do this, I'm using such a bending beam. In the test setup, the beam sits on 2 fixed points, and in the middle, at the third point, force gets applied, in my case by putting weights into the bucket. From the top, a dial indicator can then be used to measure how far the sample bends. The bending modulus in megapascals can then be determined using a formula based on the deflection and the surface moment of inertia. The higher this value, the stiffer the material and therefore the less elastically deformable. I came up with a bending modulus of about 1900 megapascals, and the comparison shows that the stiffness of PHA is similar to that of PETG. Compared to regular PLA, this is relatively low, yet totally fine for most applications. I think PHA could be stiffened by adding some natural fibers like wheat, wood, coffee grinds or similar. I sent these suggestions to Mitch and he told me that they are actually experimenting with such natural fillers, so I'm highly looking forward to that. Before we get to the impact resistance test, a quick message from today's sponsor, PCBWay, your go-to source for not just PCBs but also 3D printing, injection molding, sheet metal fabrication and CNC machining services. I recently designed a custom nozzle for ironing and used their services to get it turned from copper. I just uploaded my CAD design in their online configurator and selected the desired material and tolerance preferences. The system allowed me to track every step of the production, and a couple of days later, I received this package with my nozzle. It turned out perfect and fits as intended. So whether you're prototyping a new product, creating custom parts or working on a finished product, PCBWay has you covered. Head over to PCBWay.com, first link in the video description, and get a new user discount. Thanks to PCBWay for helping me keep such tests independent. Now back to PHA. The toughness of a material can be analyzed using an impact resistance test. It's relevant for impact-like loads. A good example here is a quadcopter frame, which also crashed occasionally. Standard materials such as PLA or PETG are not really impact resistant. PHA, on the other hand, is. The test shows that it has an impact resistance of about 20.4 kilojoules per square meter, according to my test, which is of course not an official testing device. PHA has 4 times higher impact resistance than regular PLA, which can be very helpful for some applications. Now to the temperature test, in which I analyzed the temperatures at which printed samples can be deformed. It is important to know this point, especially when the finished components are exposed to heat. For this, I used the bending beams from the 3-point bending test, only with 3 perimeters and 30% gyroid infill to represent realistic components. I recently got myself such a mini oven and I'm now trying to modify it with my own controller to generate heating curves. For the first step, I used such a NTC100K to measure temperature with an Arduino. For the test, I put a sample between 2 holders into the oven and made it heat up while measuring the temperature. I measured 110 degrees C when the sample failed under the load of the screw. This value is very good, similar to that of ABS and ASA. That's it with my standard tests I do with all filaments. Of course, there are way more properties that we could test, like friction or resilience, but I don't expect PHA to be special there. A really important property of a material that I don't test myself but take from the TDS is the density, as it determines the weight of finished parts and the cost per meter, which is more relevant than price per kilogram. The PHA has a density of 1.26 grams per cubic centimeter according to Polar Filament's datasheet. That's similar to PLA. The price is $39.99 USD per kilogram or 0.1 to 1 USD per meter, which makes it rather expensive. But since it's developed and made in the United States, I think it's fine to be a little more expensive than Chinese filaments. If they bring the price down, closer to $30 I think there's no real reason to complain. Another interesting property is the fact that it's a bioplastic and a natural product. By definition, it's food safe, but as you probably know, it's nearly impossible to produce actual food safe things on regular 3D printers. The layer lines and tiny imperfections trap bacteria, and most nozzles are not certified for food safe printing. Now let's finally talk about one of the main features, biodegradability. First, a quick word on PLA. It's often marketed as eco-friendly and compostable. In reality, that is only true under specific industrial conditions. Most people think you can throw PLA in the yard and it will slowly disappear. That does not really happen. In home compost, it sticks around. Additives and colorants are usually not certified for composting either. If you toss PLA in the ocean, it will not meaningfully break down. If you want a deep dive, check out CNC Kitchen's video in which he put prints from PLA and other materials in his compost. PHA is different. It's a true bioplastic. It's made by microorganisms and given the right environment, it will break down again. It has a 6691 Marine Biodegradability certification, meaning that it fully degrades in oceans, rivers and natural environments. But don't worry, regular water is not a problem. Tap water does not contain the bacteria needed for biodegradation, so your parts will not disappear when they get in touch with water. When PHA degrades, it does so at a rate similar to wood, sometimes faster depending on the conditions. I recently met Stefan from CNC Kitchen at Pruset in Prague. He told me about experiments with this exact PHA and one from ColorFab. He will post a detailed biodegradability test on his channel soon, and I will make sure to add the link in the description as soon as it's live. This topic is complex and I'm not an expert. What gives me confidence is that this filament has the certification, which is known to be strict. Ecogenesis is involved in the development, and from what I've seen, they put a lot of effort into getting the material and the documentation right. I hope I didn't bore you to death with all these technical tests, numbers and bar charts. While I think that they are very useful to compare different materials, in the end only one question really matters. What can we actually print with it? That's why I usually try to come up with some sample applications after doing the testing. Due to its high temperature resistance, PHA could be used as a more eco-friendly and healthier alternative to ABS. I'm thinking about car accessories or enclosed printer parts for DIY machines like Voron or Redrick. Because PHA is a bioplastic and non-toxic, I think it's also suitable for toys and things children can get in touch with. With those fancy shiny filaments, you never really know what toxic additives or colorants are in there. PHA prints seem to be comparable to wooden toys, which are generally considered the safer choice. And if you care for environmentally friendly plastics or are a company that makes a lot of prototypes that are meant to be thrown away, it might make sense to use PHA as a true eco-friendly option. Summary: I had high expectations for Polar Filament's PHA and it mostly delivers. It's a great filament, but it's not the best or ultimate fix for every 3D printing problem. No filament is. If they can bring the price down and maybe add natural fibers, it could become a highly competitive material and take a bigger share of the market soon. As always, I'd love to hear your thoughts in the comments. I read all of them and I'm super happy about your feedback and ideas. Big thanks to my channel members for supporting my work. If you want to support the channel free of charge, consider using the affiliate links and codes in the description. Thank you. Stay curious and see you next time here at JanTec Engineering.